Welcome to cybersecurity under pressure. Real attacks, real lessons. Every breach starts with something small. A trusted login, a missed alert, a system no one thought could matter. Here, we follow the incident. How it began, how it moved, what broke under pressure, and what security engineering and business teams should learn before the next one. Because the next attack will not wait for a perfect plan. Now, let's follow the evidence.
So the guy looks at the logs, right? And I kid you not, the default password for this entire water treatment facility's remote access was, it was literally just the word admin spelled backwards.
Oh no, NIMDA.
NIMDA, yes.
Which is, it's so incredibly ironic because NIMDA was that massive, globally destructive computer worm back in, the early 2000s?
Yeah.
It's like they were actively trying to tempt fate.
Right, or just like taunt the universe.
Yeah, pretty much.
It's the kind of thing you'd absolutely laugh at if it wasn't connected to, a municipal water supply that thousands of actual human beings drink from every day. Just unbelievable. But anyway.
Yeah.
You know what I've been thinking about this week? The story of an incident that started with a technical alert and ended with a lesson that every CISO should be asking about.
Oh yeah. It is definitely a story that forces a complete ground-up recalibration of how we think about digital defense. Because the old models, they simply do not apply anymore. We are in completely uncharted territory.
Exactly. And that's our mission for this deep dive. We are going to explore the terrifying collision of operational technology, artificial intelligence, and physical infrastructure.
The physical aspect is what really changes the game here.
It changes everything. We're going to be unpacking the latest directives, specifically looking at the April 2026 CISA guidance. And we're putting that alongside some incredibly dense but honestly fascinating intelligence reports from Suzu Labs and Shieldworks.
Plus the historical context.
Right. Plus we're looking at some truly sobering historical postmortems from NIST and ANISA. So for everyone listening, I want you to imagine you are sitting in the control room of a major power plant. We're looking at what happens when the digital world violently impacts your physical reality.
And we really, really need to emphasize that word violent, because when we talk about operational technology, or OT, we aren't talking about losing access to your email for a few hours.
Or like a customer database getting encrypted and you have to pay a ransom.
Exactly. This isn't data loss. We're talking about the kinetic world. We are talking about massive blast furnaces, robotic manufacturing arms swinging around, national rail networks, petrochemical refineries.
The big...
The stakes are fundamentally different because the consequences, they aren't measured in lost revenue. They are measured in environmental disasters and, quite frankly, human lives.
Yeah, which is a very heavy place to start, but we have to set the table.
Yeah.
So let's start at the foundation of how these places used to be protected, which, ironically, is a foundation that essentially no longer exists.
The air gap.
The air gap. For decades, the entire defense strategy for these massive physical systems was just this one concept. And the logic was incredibly straightforward, right? You don't plug the nuclear plant or the water treatment facility into the public internet. Problem solved.
That was the premise, yes. The core assumption for the longest time was that your IT network, so your corporate emails, your billing systems, the HR portals, that entire world was completely, both physically and logically, severed from your OT network.
They were two different planets.
Completely different planets. The OT network is where you find the control loops, the supervisory control and data acquisition stuff, the SCADA platforms, and the programmable logic controllers, the PLCs.
And for anyone who isn't deep in the engineering weeds, those PLCs are basically just specialized, heavily ruggedized computers, right?
Yeah, exactly. They are the brains on the factory floor that actually send the electrical signals to open a physical valve or spin up a turbine. And the air gap meant there was literally no wire connecting those sensitive PLCs to the corporate Wi-Fi or the outside world.
Right. But if you walk onto a factory floor today, that air gap is a total myth. It's completely collapsed. And the crazy part is, it wasn't hackers who destroyed it. It was the executive.
Oh, absolutely. It was the C-suite pushing for what they call Industry 4.0.
Which sounds great in a boardroom.
It sounds fantastic in a PowerPoint presentation. It was this relentless drive for efficiency and data-driven decision-making. Imagine you are a plant manager today. You have Executives constantly demanding real-time predictive maintenance, remote monitoring capabilities, automated supply chain integration.
They want all the data, all the time.
Exactly. And if you want a cloud-based artificial intelligence to analyze vibration data and predict exactly when a specific ball bearing inside a multi-million-dollar turbine is going to fail, well, the acoustic sensor on that bearing must eventually send its data out to the cloud.
It has to have a path out.
Right. You cannot have localized analytics anymore. The business demanded connectivity, so the engineers bridged the air gap. They ran the cables.
Yeah, I mean, my toaster apparently needs a direct Wi-Fi connection to brown bread properly now, so of course the critical cooling pumps at a chemical plant need to be accessible from some vendor's smartphone in another country.
It's the exact same underlying logic, just with catastrophic consequences.
It's just we've willingly traded existential security for, like, dashboard convenience.
It is a pretty bleak way to look at it, but operationally, that is exactly what happened. We basically punched a million tiny holes in the fortress wall just to let the data out without ever really realizing what could come back in through those same holes.
Which brings us directly to the government's response to this mess.
Yeah.
The April 2026 CPIBOD 2604 directive.
Yes.
And from reading the sources, this isn't just another boring government memo. This is a monumental shift in federal cybersecurity policy.
It is huge. CISA basically looked at this highly connected post-air gap landscape and realized that our entire framework for prioritizing vulnerabilities was just fundamentally broken.
Because of the CVSS scores, right?
Yeah.
It's the Common Vulnerability Scoring System.
Exactly.
If you're a security engineer, you live and die by these numbers. A 10 out of 10 means you drop whatever you're doing, you cancel your weekend, and you fix it.
Under the old context, that's exactly how it worked. A severity rating of, say, a CVSS 9.8 was treated as a hair-on-fire emergency across the board, completely regardless of the actual context of the device.
Which makes no sense when you think about it physically.
Right. Think about the physical reality of a network. A 9.8 vulnerability on an isolated internal database that's sitting in a locked basement on a segmented VLAN that received the exact same urgency as a 9.8 vulnerability on a VPN gateway that has a direct internet connection and is actively being scanned by threat actors in the wild.
Which means federal agencies who, let's be honest, always have limited time, limited budgets, they're understaffed, they were running around patching the wrong things first.
Constantly.
They were treating a theoretical risk in a locked vault the same as, like, a burglar actively kicking in the front door.
That categorization mismatch was a massive operational vulnerability in and of itself. I mean, defenders were completely exhausted from alert fatigue. They were patching low-risk internal assets while their internet-exposed critical infrastructure just sat there wide open.
But the CISA directive explicitly changes that dynamic, right?
Right.
It forces a 3-day critical patch mandate specifically for those internet-exposed assets facing AI-driven threats.
It does.
But wait, I have to push back here because reading that made me crazy. How can any organization patch perfectly in 3 days? I mean, think about it from the perspective of an operator on the floor.
It's a huge ask.
In a normal IT environment, forcing a patch in 72 hours is hard enough. But in an OT environment, patching a programmable logic controller might mean shutting down a continuous manufacturing line.
Yes, it absolutely might.
It requires scheduled downtime, safety reviews, vendor approvals to make sure the patch doesn't break the warranty. 3 days isn't just aggressive. In the OT world, it sounds clinically insane.
From a legacy operational standpoint, you are completely correct. It sounds impossible. The engineers are probably tearing their hair out over it. But it is a necessary, almost desperate reaction to the reality outlined in the Suzu Labs intelligence reporting.
Okay, let's get into the Suzu Lab stuff because this blew my mind.
The Suzu Labs analysts point out a terrifying metric. They found that the mean time to exploit has actually gone negative.
Okay, stop. You have to explain the mechanics of that. Because logically, how can a timeline be negative? You can't exploit something before it exists.
It sounds like time travel, but it comes down to how artificial intelligence has fundamentally weaponized vulnerability discovery. Let's look at the old model for a second.
The way things used to work.
Right. A software vendor discovers a flaw, they release a patch on, say, a Tuesday, and then human attackers would take weeks, or sometimes even months, to reverse engineer that patch, figure out what changed, and manually write an exploit to take advantage of the systems that hadn't applied the patch yet.
Right, so the defenders had a head start, the clock started ticking, but they had a buffer?
Exactly. But now, adversaries are feeding those patch binaries directly into AI models designed for automated binary diffing.
Automated diffing, okay.
The AI compares the old vulnerable file with the new patched file. It instantly maps out the exact assembly code that changed. Perhaps, a new memory bounds check was added by the developer.
So the AI immediately sees where the Band-Aid was placed.
Exactly. The AI instantly understands that the old version has a buffer overflow vulnerability at that specific memory address. It then uses a large language model to trace the execution path back to a user input field, and literally within hours, it automatically generates a Python script to send a maliciously crafted payload to execute shellcode.
Wow.
They are weaponizing the flaw before the defenders even have time to download the patch, let alone test it in a sandbox environment to see if it breaks the factory line. The attackers are moving faster than linear time allows a human security team's change advisory board to react.
So they are getting hit before the meeting about the patch even happens.
Exactly. Hence, negative time to exploit.
That is deeply, deeply unsettling. And the proof isn't theoretical here. It's already in the wild, like the March 2026 Strucker cyber attack.
Yes, the medical technology giant. A cyber attack wiped devices across 79 countries simultaneously.
79 countries at once.
That is the true scale and speed of AI-driven exploitation. It wasn't a slow, creeping infection where you see one server go down in London and then another one goes down a day later in Tokyo. It was a global, synchronized wipe executed the exact moment the vulnerability was mapped by the AI.
So if you're a CISO, and the exploit window is measured in hours, but CISA says you have 3 days to patch, you're technically already behind before the clock even starts.
You are.
But here's where it gets incredibly nuanced with this mandate, and I think a lot of people miss this. The CISA directive doesn't just blindly say, deploy the patch in 3 days. It mandates a 3-day window to conduct mandatory forensic triage before applying the patch.
This is the most crucial and often entirely misunderstood part of the directive. It speaks to a very specific documented operational risk. If you have an internet-exposed system that has been vulnerable for even a few hours in this new AI paradigm, you must assume it has already been compromised.
You have to operate under the assumption that prevention has already failed, which is a really bitter pill for traditional network defenders to swallow, right?
Yeah.
They want to believe their firewalls are working.
It is, but look at the mechanics of an attack. If you just blindly apply the patch on day 2, what are you actually doing from a technical standpoint?
You're just updating a file.
You are overwriting the vulnerable executable with a secure one and usually rebooting the system. But you aren't checking if the adversary is already inside the operating system. If the system is already backdoored, patching without investigation simply allows the adversary to maintain their persistence.
Because they've already moved laterally.
Exactly. During that brief window of vulnerability, the automated exploit might have dropped a rootkit deep into the kernel, or created new, unauthorized administrative credentials in Active Directory, or even modified the firmware of a network card.
And a patch doesn't look for any of that.
None of those things are fixed by patching a vulnerable web service. The malicious implants will easily survive the patch cycle and the subsequent reboot.
I was trying to think of a way to visualize this while I was reading the reports. It's like discovering your front door lock is broken, right?
Yeah.
If you just blindly replace the lock on the front door, you've secured the perimeter, but you haven't checked to see if the killer is already upstairs in the guest bedroom.
That is...
You actually just lock yourself inside with them.
That is a very visceral analogy, but mechanically it is spot on. The CISA mandate forces defenders to shift the fundamental question. Instead of asking, how quickly can we push this patch? Security teams must now ask, can we prove this system wasn't compromised during the exposure window?
You have to prove the negative.
You have to hunt continuously through the logs and the memory space. You have to compress the dwell time of the attacker. As the Suzu Labs report concludes, the organizations that survive this new era won't be the ones that patch perfectly.
Because you can't.
Nobody patches perfectly at -7-day speed. The survivors will be the ones who assume exposure, conduct the forensic triage, and use their own defensive AI to scale their hunting capabilities inside the network.
But wait, this brings up a massive, glaring logistical problem for Chapter 2 here.
Oh, the visibility issue.
Yes. To patch a system in 3 days, or even to perform forensic triage on it, you have to actually know it exists in the first place. And from what Dan Ricci points out in the Clarity Nexus insights we reviewed, most plant managers are operating off of glorified Excel spreadsheets.
It is terrifyingly common.
How do you patch a phantom asset? You can't secure what you don't know you have.
You don't. And that is why visibility is the absolute foundation of any cybersecurity program. But in operational technology, visibility is an absolute minefield.
Dan Ricci, the ICS advisory founder, he makes a phenomenal point in that CyberScoop white paper. He argues that a simple list of assets, like that spreadsheet that has been updated since 2024, is not a true asset inventory.
Not even close.
He calls it an illusion of control.
And he's right. A static list is obsolete the moment you hit save. Think about a modern factory floor. Devices are constantly being swapped out for maintenance, IP addresses shift around, contractors walk in and plug temporary diagnostic laptops into the switches.
It's a living environment.
It is. A true inventory must be dynamic, organized, constantly updated, and physically validated. It has to tell you not just what the asset is, say, a Siemens PLC, but its current firmware version, its configuration state, its exact physical location in cabinet 4 on the plant floor, and its network dependencies.
Like, who is it talking to and who is allowed to talk to it?
Exactly.
So I was looking at traditional IT scanning tools, right? The stuff you'd use on a corporate network to build that dynamic inventory, and thinking about applying them to an OT environment. And it feels like trying to secure a hospital by sending a heavily armed SWAT team to aggressively shake every single door, window, and medical monitor to see if they're locked.
That is a great way to picture it.
Yes, you might find the unlocked doors, but you're going to accidentally unplug a bunch of life support machines in the process because you're being so aggressive.
The mechanics behind that analogy are shockingly accurate, and the NIST OT's security guide actually provides the historical receipts to validate it.
Tell me about the historical stuff, because this blew my mind.
So active scanning using a tool like an NAMP scan to map a network is standard practice in corporate IT. IT systems use robust protocols like TCP/IP, and they are designed to gracefully drop unexpected or malformed packets. If a server gets a weird ping, it just ignores it.
Right. It's built for the noise of the internet.
But OT devices, especially legacy ones built 20 years ago, were never designed to handle unexpected network negotiation.
They're incredibly fragile.
Extremely fragile. Legacy devices often run on primitive real-time protocols like Modbus or DNP3. They have tiny microcontrollers with very, very limited memory buffers. NIST documents this horrifying accidental event where a well-meaning security team was performing a routine ping sweep on an active SCADA network.
And a ping sweep is basically just a network tool sending a message asking, "Hello, are you there?" to every IP address in a range, right?
Yes. Just an ICMP echo request.
Just a digital knock on the door, nothing malicious at all.
Right. But this specific network they were scanning controlled a dormant 9-foot robotic manufacturing arm.
Oh, man.
The controller for the arm received the ping sweep. Because it lacked a modern networking stack, it literally didn't know how to process the unexpected protocol negotiation. The tiny memory buffer on the controller overflowed, the CPU spiked to 100%, and the system seized up.
Just from a ping.
Just from a ping. And when these industrial systems seize, they often default to a hard-coded failsafe state. In this case, for whatever reason, the failsafe was an active state.
Wait.
The dormant 9-foot robotic arm suddenly swung 180 degrees at full speed across the factory floor.
Oh my God.
Yeah.
If anyone had been standing in the operational envelope of that arm, it wouldn't have been a cybersecurity incident. It would have been a fatal industrial accident.
Exactly. The kinetic impact of a digital scan. And that wasn't an isolated incident. NIST details another event where a similar active scan was run on an ICS network in a semiconductor fabrication plant.
Those clean rooms where they make microchips.
Yes. The system controlling the precise creation of the integrated circuits couldn't handle the malformed packets, and it hung. It just locked up mid-process. Because the environment in a fab plant must be perfectly controlled down to the chemical level, that single millisecond of digital hesitation resulted in the destruction of $50,000 worth of silicon wafers instantly.
50 grand.
Yeah.
Gone in a millisecond.
Yeah.
Just because someone in IT wanted to know what IP addresses were active on the network.
It highlights the massive cultural divide between IT and OT.
So if you are the CISO, what does this all mean for visibility? If we can't actively scan the network without breaking the blast furnace or swinging a robotic arm around, how do we actually find the assets so we can patch them in 3 days?
In industrial scenarios, passive monitoring is the required foundation. Instead of actively interrogating the devices, you use networked IPs or span ports to just listen to the ambient traffic.
I want to focus on the mechanics of that for a second, just to be clear. If you're utilizing a span port, a switched port analyzer, you are configuring a network switch to basically take a photocopy of all the traffic flowing through it and send that copy to a monitoring tool.
Correct.
And a TAP, or Test Access Point, is a physical hardware device you literally insert in line into the network cable that physically copies the light or the electrical signal.
Yes. In both cases, your monitoring tool is completely out of band. It is silently listening to the conversations already happening on the network between the HMIs and the PLCs.
It's eavesdropping.
It's safe eavesdropping. It isn't generating a single packet of new traffic. It's completely safe, passive collection. The tool analyzes the packet headers and the payloads to establish baselines for asset behaviors. It identifies connected devices, and it can even deduce firmware versions without ever directly touching the sensitive controllers.
Okay, so problem solved. We just sit back, listen to the span port, and build our dynamic inventory safely.
If only it were that simple.
There's always a catch.
Always a catch. And this is where we have to look at the massive caveat introduced in the Enhancing OT Visibility white paper. Passive monitoring is fantastic, but it relies on a fundamental law of physics. It only works if the assets are actually talking. If a device never speaks, a passive listener will never know it's there.
So you have a massive blind spot for quiet devices.
Significant blind spots. The white paper details a specific exception in the oil and gas industry that breaks the passive model entirely.
Let's hear it.
Imagine a critical, remote, programmable logic controller out on a distant, unmanned oil pipeline in the middle of the desert somewhere. It communicates back to the central SCADA system over a high-latency satellite link or a cellular modem.
Which is expensive and slow.
Exactly. To save bandwidth and power, the engineers configured it to only communicate very, very infrequently. Maybe it only sends a tiny telemetry ping once a week, or only when a pressure threshold is breached.
So your passive monitor might sit there on the network for 6 days listening and hear absolutely nothing, leading you to assume that IP address is empty.
Exactly. And even when it does communicate, those sporadic, tiny telemetry pings rarely contain the deep metadata you need. They provide incomplete firmware data, which makes vulnerability assessments and that CISA 3-day patch prioritization mandate completely impossible.
You can't patch a vulnerability if you don't know what firmware the remote pipeline is running.
Right. In those highly specific cases, passive monitoring simply isn't enough. Organizations have to use throttled, highly controlled active collection.
You have to poke the bear.
Very gently. They have to carefully query those remote PLCs using native industrial protocols to validate their critical asset firmware. It's a terrifying, delicate balancing act between the risk of not knowing what's on your network and the risk of breaking the system by asking it a question.
And when do you usually take that risk?
Yeah.
You wait for the system to be turned off. Which brings us directly to Chapter 3, the concept of planned downtime. If you have to do that active collection, or if you have to apply that 3-day critical patch that requires a system reboot, you're usually waiting for a scheduled maintenance window to do it safely.
Yes. The maintenance window, traditionally viewed by plant operators and engineers as the only safe harbor in the operational storm.
The one time you can breathe.
The one time you can actually touch the systems without risking a kinetic disaster.
But the intelligence we reviewed from the ShieldWorks report completely shatters that illusion. They reframe maintenance windows not as safe downtime, but as highly vulnerable, exceptionally high-risk cybersecurity operations.
And if you look at the mechanics of how a plant actually operates during a turnaround, they are absolutely right to reframe it.
I mean, I was laughing darkly reading this because it is the ultimate tragic irony. The exact time organizations bring their systems down to fix them, to patch them, to secure them against hackers is the exact time they are most completely blind to attacks.
It is a massive operational blind spot. Think about the physical reality of what happens during a planned plant shutdown or a major turnaround.
It's chaos.
It is organized chaos. Hundreds of pieces of equipment are taken offline. Thousands of alarms are disabled so the sirens aren't blaring constantly in the control room. Systems are being rebooted left and right. And third-party vendors, often dozens of contractors who don't normally work there, are brought in with their own laptops to update proprietary machinery.
The perimeter defenses are completely bypassed. It's essentially Swiss cheese.
It's worse than just the perimeter being porous. The internal visibility is intentionally completely compromised. The Shieldworks report details how OT monitoring tools, the very passive listening systems meant to detect anomalies we just talked about, are often literally powered down during these windows.
They turn off the security cameras, basically.
Or, if they are left on, they are manually tuned into maintenance mode. And the engineers do this because if they don't, the monitoring tool will trigger 10,000 critical alerts as contractors start disconnecting cables and flashing firmware.
And even if a security analyst is sitting there watching the screen, they are blinded by the sheer volume of legitimate, highly disruptive reconfiguration traffic.
Precisely. It creates an impenetrable digital fog. Under the cover of that fog, malicious activities can be initiated without triggering a single alarm because anomalous behavior suddenly looks completely indistinguishable from normal maintenance behavior.
The report gives some terrifying concrete examples of how adversaries exploit this exact dynamic. Let's look at the 2020 European manufacturing ransomware attack.
That is a classic example of exploiting the maintenance perimeter. In that incident, the manufacturing plant was undergoing a scheduled maintenance weekend. The local engineers needed an external vendor to dial in and patch some specialized systems remotely.
Because the vendor is in another country, probably.
Right. So they temporarily opened up remote desktop protocol RDP sessions right through the firewall, specifically for the vendor.
But they left them open and unmonitored.
Yes. Adversaries constantly scan the internet for open RDP ports. They found those temporary, unmonitored sessions, brute forced the credentials, exploited the access, and deployed ransomware across the entire manufacturing environment.
Wow.
The plant was down for weeks. The mechanical lesson there is that temporary access, even for legitimate maintenance, must never, ever be left unmonitored.
But it gets even stealthier than opportunistic ransomware, doesn't it? Look at the mechanics of the 2022 Asian refinery APT attack.
That one was an absolute masterclass in exploiting the maintenance window fog of war. Advanced persistent threat actors, an unattributed, highly sophisticated state-sponsored group, had likely been in the IT network for a while.
Just watching.
Just waiting patiently for a planned, multi-week shutdown at the refinery. They knew that during the shutdown, OT engineers would be rushing to update systems and flash new firmware onto the PLCs.
So they hid their malicious update inside the legitimate update process.
Exactly. While the engineers were pushing updates, the adversaries slipped in and inserted persistence deep into the PLC firmware itself. They wrote to the EEPROM of the controllers.
Wait, EEPROM? Deep in the actual physical hardware running the refining process? You can't just run an antivirus scan to find that.
No, you can't. And because it happened during a maintenance window when firmware hashes were supposed to be changing, the passive monitoring tools didn't flag the new code as malicious.
They just thought it was part of the update.
It just recorded it as another maintenance event. When the plant came back online and steady-state operations resumed, the adversaries had a quiet, deeply embedded foothold that went completely undetected for months. They had total control over the refining process.
Okay, I have to push back on behalf of the operators here.
Yeah.
If you're a plant manager listening to this, what are you supposed to do? You've got compressed timelines. You have immense financial pressure from the board to minimize downtime. I mean, in a large refinery, every hour you are offline costs millions of dollars in lost production.
Oh, the pressure is unimaginable.
You have dozens of vendors screaming to get their updates installed so they can move to the next job. The engineers are exhausted, working double shifts. They're naturally going to cut corners just to get the physical plant running again. You can't expect them to act like forensic analysts.
It is an incredibly high-pressure environment, without question. The stress is immense, but the Shieldworks solution is non-negotiable if you want the plant to remain secure in this threat landscape. You have to fundamentally reframe the culture around the maintenance window. It cannot be viewed as relaxing downtime.
It's not a break.
No. It must be treated as a high-risk pre-incident scenario with heightened situational awareness.
So you treat the maintenance window with the exact same security posture as you would an active cyber incident response.
Exactly. Every single contractor's laptop needs to be scanned before it connects. Every temporary remote access port needs a strict, time-bound security baseline. But the real mechanical key to solving this is in the aftermath. Shieldworks outlines mandatory post-maintenance threat hunting.
Because you can't just flip the switch back on.
You cannot just flip the switch, turn the plant back on, and hope for the best.
You have to clear the fog.
You have to systematically validate every single configuration change against the planned work orders. If your monitoring tool says a PLC firmware changed on Tuesday at 3 a.m., you cross-reference that with the ticketing system.
You check the receipts.
You verify who changed it, why they changed it, and you validate the cryptographic hash of the new firmware. If there is a change without a ticket, you treat it as a hostile breach immediately. Post-maintenance threat hunting isn't optional anymore. It is the only way to ensure you haven't brought an attacker back online with you.
And if that fog isn't cleared, if an attacker does slip through during maintenance, the consequences bleed rapidly out of the network cables and into the physical world. Which leads us to Chapter 4. Let's move to the structural defenses that are supposed to prevent that. We've talked about the vulnerabilities in time, the maintenance windows, but what about the structural vulnerabilities of the network architecture itself?
This is where we look to the IEC 624443 standard, which is globally recognized as the foundational framework for industrial cybersecurity architecture. The core philosophy of this standard relies heavily on two specific concepts: zones and conduits.
Right, let's define the mechanics of these clearly for anyone who might be designing a network. A zone is a logical or physical grouping of assets that share common security requirements.
Correct. For example, you wouldn't put a general-purpose engineering workstation in the same zone as a critical safety controller. You might group all the human-machine interfaces, the HMIs, which are the touchscreens the operators use, into one zone. Then you group the critical safety programmable logic controllers into an entirely different zone because the safety controllers require a massively higher level of protection.
The stakes are different.
Exactly. If the HMI goes down, you lose visibility. If the safety controller goes down, the plant explodes. They cannot share the same security posture.
And the conduit is the logical grouping of communication channels that protects the data flowing between those zones. It's the pipe connecting the rooms. But how does this actually work in practice? Like if I'm a network architect building this out, what is the physical or logical reality of a conduit? It's not just a cable, right?
No, it depends entirely on the security levels, or SLs, of the zones being connected. Let's contrast two different implementations to make it concrete. If you have a conduit connecting two zones that share the exact same security level, say connecting one group of HMIs to another group of HMIs, you might implement a transparent logical gateway.
Okay, what does that do?
This acts like a protected pipe. Data flows relatively freely, but the conduit ensures the integrity and confidentiality of that data in transit, perhaps using IPsec encryption or host identity protocols to ensure no one is spoofing the packets in the middle.
Okay, that makes sense for peer-to-peer lateral traffic. But what if I need to connect the corporate IT network, which is a fundamentally low security level full of phishing emails and web browsers, to the plant floor controllers, which are a high security level?
In that scenario, a transparent gateway is completely unacceptable. For a transition between a low security zone and a high security zone, your conduit must implement an application layer gateway, or ALG.
How's that different from a normal firewall?
This isn't just a firewall looking at IP addresses and port numbers. It acts as a highly restrictive, deep packet inspection filter. It cracks open the industrial protocol packets. It inspects the traffic at the application layer, ensuring only specific, pre-approved commands are allowed to cross the boundary.
So it actually understands the industrial language.
Exactly. If the protocol is Modbus, the ALG knows the difference between a read coil command and a write coil command.
Oh, that's clever.
It can be configured to allow the corporate IT network to send a read command to check the temperature of a sensor for a dashboard, but it will absolutely drop and block any write command attempting to change the temperature set point. The conduit strictly enforces the segmentation at the command level.
And when that strict segmentation fails, or when a network is built without it entirely, it truly is a matter of kinetic destruction. The historical postmortems from NIST and ANISA that we reviewed are chilling because they show the physics of what happens when zones bleed together. Take the 2014 German steel mill attack.
That incident remains a watershed moment in OT security because of the sheer scale of the physical damage.
Walk us through it.
Hackers breached the corporate business network first, most likely through a Standal's social engineering tactic or a spear phishing email targeting an office worker. But because the network wasn't properly segmented with strict conduits and ALGs, the attackers didn't hit a wall.
The zones bled together.
They were able to pivot directly from the IT network down into the production networks running the steel mill.
And once they were in the production network, they didn't just steal data, right? They manipulated the control systems.
They systematically disrupted the control components of a massive blast furnace. And we have to understand the physics of a blast furnace to really understand the consequence here.
Yeah, paint a picture for us.
A blast furnace operates continuously at temperatures exceeding 2,000 degrees Celsius, smelting iron ore. If you stop the cooling systems, or if you halt the extraction process abruptly, the molten iron inside will begin to cool and solidify.
It turns into a 500-ton solid block of iron inside the furnace.
Yes, what the industry calls a salamander. It essentially destroys the furnace from the inside out, requiring months of explosives and jackhammers to clear.
Wow.
The attackers disrupted the control systems to such a severe degree that when the plant operators realized something was wrong and tried to perform a standard controlled shutdown of the blast furnace to save it, the system failed to respond.
The brakes were out.
The automated safety sequences were corrupted, the furnace could not be shut down properly, resulting in massive, catastrophic physical destruction to the facility.
The malicious code physically broke the mill. And then there's the 2017 Triton attack on the Saudi petrochemical facility. This one is particularly insidious, arguably more evil, because it didn't just target the main process controllers, it specifically targeted the safety systems.
Triton is the absolute nightmare scenario for any industrial engineer. In any hazardous industrial environment, you have the distributed control system, the DCS, which runs the day-to-day process. But completely separate from that, you have a safety instrumented system, or SIS.
Like a physical watchdog.
The SIS operates independently of the main process controllers. It monitors the physical state of the plant. If the main process goes out of control, if pressure builds up too high in a pipe, or temperatures spike towards an ignition point, the SIS acts as the autonomous last line of defense to trigger an automatic safe shutdown before an explosion occurs.
And the hackers bypassed the main process and specifically wrote custom malware to compromise that safety system.
Yeah.
They wanted to blind the watchdog.
Yes. The attackers compromised an engineering workstation and used a proprietary protocol to deploy malicious software that reprogrammed the Triconex safety controllers. These controllers use a sophisticated triple redundant processor architecture.
How does that work?
3 independent microprocessors all process the same data and vote on the outcome. If 2 vote that the plant is safe and 1 votes it isn't, the 2 outvote the 1. It's designed for extreme physical reliability.
But the malware tried to rewrite the logic on all 3 processes at the same time.
Exactly. Fortunately for the facility, the attackers made a slight coding error. This error caused a timing mismatch in the execution of the malicious code across the redundant processors.
So they tripped over their own shoelaces.
They did. The processors realized they were out of sync, triggering a hard-coded fail-safe state. This caused the plant to autonomously shut down safely before the attackers could execute their ultimate payload.
Thank God.
But the intent of Triton was undeniable. Quietly disable the safety system, wait, and then cause a catastrophic physical explosion on the main process without the SIS there to stop it.
It's pure malice.
Yeah.
And the vulnerability isn't isolated to manufacturing or oil and gas.
Yeah.
ENISA, the European Union Agency for Cybersecurity, outlines similar, highly destructive threat scenarios for national railway networks. We aren't just talking about a single plant anymore. We are talking about sprawling infrastructure.
The ENISA report details how a lack of strict segmentation could allow malware introduced via a simple phishing email in a rail operator's corporate office to propagate into the operational technology systems of the rail network itself.
The signaling systems.
They describe scenarios where adversaries could manipulate the traffic supervising systems, injecting malicious shellcode that disrupts the automatic train protection, or ATP, signals. The ATP is what physically prevents trains from colliding. If you disrupt it, the fail-safe is an urgent emergency halt of all train traffic across the network.
You completely paralyze the logistics of a nation.
Instantly.
And even if they don't hit the trains directly with malware, Elisa points out that unsegmented, internet-exposed systems are incredibly vulnerable to brute force disruption. They highlight scenarios where botnets launch massive distributed denial of service, or DDoS, attacks against internet-facing railway ticketing, scheduling, and routing services. You don't actually have to derail a train to shut down a transit system. You just have to take down the digital systems that allow people to buy a ticket or know what track the train is on.
Exactly. The kinetic impact is achieved through digital congestion.
But there's an entirely different layer to this structural vulnerability, one that is brilliantly highlighted by the engineering experts at eTech Group. In cybersecurity, we focus so heavily on digital malware, the Russian hackers, the ransomware gangs, that we completely forget the physical network infrastructure itself is often failing invisibly.
Yes, invisible physical network failures. E-Tech Group points out that unexpected network slowdowns, packet loss, and these ghost communication errors on the plant floor often have absolutely nothing to do with the cyber attack and everything to do with the hostility of the physical environment.
Because it's not a pristine server room.
Industrial environments are fundamentally hostile to delicate electronics. A corporate server room is climate-controlled and pristine. A factory floor is not. E-Tech Group notes how ambient heat from blast furnaces and microscopic factory dust slowly degrade network switch components and choke cooling fans over years.
And the vibration.
Furthermore, the constant low-frequency vibration of heavy machinery like massive stamping presses or turbines literally loosens the physical Ethernet and serial cable terminations in the network racks.
And electrical noise, right? The electromagnetic interference, or EMI.
EMI is a massive factor. When you have massive industrial motors running nearby, they generate huge electromagnetic fields. This interference can actually corrupt the digital signals, the ones in rees traveling inside the unshielded network cables. It causes cyclic redundancy check, or CRC errors. Packets get dropped or malformed.
It creates this vicious feedback loop of failure.
It does.
Because the physical degradation of the cable causes digital packet loss. The packet loss degrades the reliability of the control loops between the HMI and the PLC. The degraded control loop leads to unstable physical processes, which causes more vibration, which loosens the cable further. It proves that in OT, digital and physical reliability are completely deeply intertwined. A loose vibrating wire can mimic the exact symptoms of a cyber attack, and a sophisticated cyber attack can exploit the instability caused by a loose wire.
Which makes governing and defending these systems incredibly complex. The defender is fighting both nation-states and the laws of physics simultaneously.
And it's only going to get harder as we add more autonomy. Let's move into the final chapter of our discussion, exploring the future of OT defense. We've talked about AI as an offensive weapon, the negative time to exploit, but AI is also being rapidly integrated into OT defense and daily operations.
The CISA OT Zero Trust guidance tackles this emerging reality head-on. Utilities, manufacturers, and logistics companies are heavily integrating artificial intelligence into their environments to manage processes that are simply too complex for human operators to optimize.
Like what?
They are using machine learning models for predictive maintenance, analyzing massive data sets of acoustic vibrations to predict exactly when a pump will fail days before it happens. They're also using AI for autonomous load balancing on power grids, dynamically routing electricity based on real-time demand.
And crucially, they're using AI-based security platforms to monitor the network traffic we talked about earlier. The AI listens to the span ports and learns what is normal so it can detect the anomalies.
Right.
But there is a terrifying concept buried in the CISA guidance regarding these defensive AIs, and it's called model drift.
Model drift is arguably one of the most insidious, invisible threats in modern OT environments. To understand it, you have to understand how machine learning actually works.
Break it down for us.
When you train an AI model to detect anomalies on a factory floor, you train it on a baseline of normal data. The AI builds a complex mathematical model of what the network and the physical processes look like when everything is fine. But in a physical industrial environment, normal is always changing.
Right, because of the physical degradation we just talked about.
Exactly. Equipment ages. Bearings slowly wear down, causing their acoustic frequency to shift slightly. Seasonal temperature changes alter the fluid dynamics of a pipeline, changing the pressure signatures. A new contractor installs a slightly different brand of sensor.
It's never static.
Day by day, month by month, the real-world operating conditions slowly diverge from the original static distribution of the AI's training data.
So the AI's accuracy degrades. It's looking for a baseline that no longer physically exists. Think of model drift, like the magnetic deviation on a ship's compass.
That's a great way to think about it.
The compass isn't broken. The needle is still pointing to what it mathematically calculates as north. But because the magnetic field around the ship has slowly changed over the years, the compass's north is now 3 degrees off from true north. If the navigator doesn't recalibrate it, you smoothly sail your ship straight into a coral reef, all while the sophisticated instrument panel tells you your heading is perfectly fine.
That is a phenomenal analogy because it highlights the core danger. It degrades silently. When an AI model drifts, it doesn't throw a blue screen of death. It doesn't sound an alarm. The degradation manifests as incrementally less reliable predictions.
So you don't even know it's failing.
An OT security platform whose underlying ML model has drifted might continue to report 99% confidence scores to the dashboard, assuring the CISO that the network is secure. Meanwhile, its actual mathematical ability to detect a novel, subtle threat has completely eroded.
It's a total false sense of security. You are completely defenseless against a sophisticated attacker, and absolutely no one in the control room knows it. So how can an organization possibly govern this kind of invisible mathematical threat? You can't just install an antivirus program for model drift.
CISA provides a very specific structural recommendation here: true cross-functional fluency. Historically, the IT security team, the OT engineering team on the plant floor, and the data science team building the AI operated in completely separate silos.
They didn't even talk to each other.
They didn't speak each other's languages, and frankly, they often didn't like each other.
Because IT cares about data confidentiality and patching. OT cares about physical safety and keeping the line running at all costs. And data science cares about algorithmic accuracy and data purity. They have fundamentally conflicting priorities.
Exactly. But CISA states that to govern AI and OT, these groups must collaborate at the policy level, continuously, not just when a crisis hits during an incident response. The communication loop must be tight.
Give me an example of what that looks like.
For example, if the OT engineer replaces a physical pump with a slightly different model, they have to proactively tell the data scientist. The data scientist then knows they must retrain the AI model on the new acoustic baseline of the new pump.
And if they don't?
If they don't communicate this, the security team's dashboard is going to suddenly get flooded with false positives because the AI thinks the new pump's sound is an anomaly, or much worse, the AI model adjusts itself poorly and creates false negatives, accepting a Stuxnet-style physical manipulation as normal wear and tear.
Which is terrifying.
Genuine, continuous, cross-functional fluency is the only way governance frameworks actually shape the physical risk posture of the plant.
It's about breaking down the cultural silos to build actual operational resilience. And that concept of resilience brings us to the Nordal philosophy outlined in our final source text. Nordal emphasizes a very hard, uncomfortable truth for the cybersecurity industry.
What's that?
Perfection is impossible.
It is the hardest truth to accept, but the most necessary. If the exploit window is negative because of AI weaponization, if active scanning breaks the factory, if maintenance windows are a vulnerable fog of war, and if your AI defensive model is silently drifting out of accuracy, you mathematically cannot guarantee prevention.
The fortress will be breached.
The fortress will absolutely be breached.
So what does resilience actually mean then, if not keeping the bad guys out?
Resilience means accepting the inevitability of the threat. It means assuming the adversary will bypass the perimeter and designing your architecture to minimize the physical impact of that breach and ensuring you can recover operations quickly and safely.
Which ties back to the logs.
It ties directly back to the Clarity Insights and the IEC 62443 standards, specifically Requirement 6.1 audit log accessibility.
Because if you don't have robust, read-only, tamper-proof audit logs aggregated in the central location, you cannot perform the forensic triage that CISA mandates in that 3-day window.
Precisely. You can't clear the fog of the maintenance window without logs. If a PLC goes down and you don't have the logs to tell you whether it was a network packet overflow, a loose cable, or a Russian APT injecting firmware, you don't know what happened.
You're blind.
And if you don't know what happened, you don't know how to recover safely. You might reboot a compromised system and trigger the destructive payload.
Resilience is built on the assumption of failure. It is continuous AI-assisted threat hunting. It is rigorous physical and logical segmentation with application layer gateways. It is cross-functional communication between the engineer and the data scientist. And above all, it is an unwavering, obsessive commitment to visibility.
It is a completely different paradigm. We aren't building an impenetrable static fortress anymore. We are building a ship with enough intelligent, watertight compartments to stay afloat, navigate the damage, and keep moving forward even after it takes a direct torpedo hit.
That's all for this episode of Cybersecurity Under Pressure. Real attacks, real lessons. Check your systems, check your assumptions, and maybe, just maybe, question whether the AI model or the air gap you trusted yesterday is still reliable today. See you in the next chapter.
You have been listening to Cybersecurity Under Pressure. Real attacks, real lessons. Real incidents leave real lessons. Stay prepared, stay critical, and keep following the evidence.